In this video, we're going to be talking about some of the features of simple linear regression, in addition to how we can actually find the best estimates of the model parameters possible. First of all, it's important to note that the errors in a simple linear regression model are independent and identically distributed. Thinking about what these mean, independent means that the size of one error or the direction of one error doesn't impact the other errors. You can think about how if we had a model where we included lots of brother and sister pairs, that the error from a brother or a sister may be more similar to the error found in their other brother and sister than it would be to a random stranger. This is a great way to think about independence in a statistical model, and we want to avoid that as much as possible if we don't have the model constructed to account for those pairings. Identically distributed just means that, as we showed in the previous video, when we have those little normal curves, they don't change from one place to the other. Those normal curves are identical in the entire range of the values that they're looking at. This idea is usually denoted IID and can be written, and I can't write this unfortunately on my computer because I'm not talented enough, so we'll go to this little blackboard. In the same way that we had the errors written earlier, that is the epsilon as distributed as a normal with a mean of 0 and a variance of sigma squared, you'll see a little IID written over the distribution to indicate that they are independent and identically distributed. So that's how we denote that idea. Incidentally, this has another implication that I suppose we can write out here. That is that the y values are independent and identically distributed as a normal. Now this may strike you as strange, but if you are taking mathematical statistics, you'll remember that the distribution of a value depends solely upon any random components. So since epsilon is the only random component for y, and epsilon is distributed normally, independent identically distributed, then the y's are going to be distributed normally, independent identically distributed. Now thinking about what the average value of the y's is, recall that we looked at the expected value of y, and the expected value of y was beta 0 plus beta 1x. So that's going to be our average of the y's, not 0 but beta 0 plus beta 1x. And then the variation, well, there's no variation in a constant. The only variation is going to come from the random component, that error term. So the variation is going to be identical to that error term. And that's how we can come up with our distribution of the y values. Notice that we have several different parameters that need to be modeled from the data. And again, that's one of the things that we're going to talk about today. So we have all of our Greek letters need to be found from the data. Excuse me, not epsilon. Epsilon changes with each value, but sigma squared, the overall variance of the epsilons, can be found. So this is our slope, our intercept, and then our error term, or the variance of our error term. All need to be estimated from data. The estimates for these are written as b sub 0 instead of beta sub 0, b sub 1 instead of beta sub 1, and s squared. And if you remember back to your basic statistics course, you'll remember that our population variance was sigma squared, our sample variance was s squared. So once we estimate things from the data, we start to use the Latin letter notation instead of the Greek letter notation, and you'll see this throughout our statistical models. So all of these Latin letter notations in this line are going to be from the data, and we're estimating these. We can also express fitted values, or our estimates. That's our best guess from data, through the use of what we call hats. So we could have beta 0 hat, which literally just puts a little hat on top of it. Beta 1 hat and sigma squared hat. All of these are also ways that we could write B0, B1, and S squared. So betas, the betas in our sigma, these are all of our theoretical values that are true in the population of data in that whole world if we had all the data in the world. But we're never going to know it because we're never going to get all the data in the world. As soon as we collect a sample and make a guess at these values, we switch to either this notation, which is the Latin letters, or this notation. Both of these mean exactly the same thing. It just depends on kind of which one's easier to write at the time is which one I will go with. There is an exception though, and the exception is a very common case where we will write y hat as an estimate of y. So let's say we were creating a model for prediction and we wanted to make our best guess at what the outcome is going to be. We would call that best guess y hat. That's our guess as to the outcome. Thus, the equation we'll get on fitting a model is our best guess y hat equals b0 plus b1 x. This is our best guess. Now we can write this in general, that's what we do have. For an individual prediction, we can have x sub I and y sub I for a prediction with each of these values specifically. But this is our very, very best possible guess as to what the outcome is going to be, is our guess at the intercept from the data, our guess at the slope from the data, times whatever the x value is. Note that we can do this same notation, except we can take these betas with their hats instead. So we could also write this as beta 0 hat and beta 1 hat if we'd prefer. You'll see me use both, but I will probably tend to use this notation. Y hat is very common, so you'll see y hat a lot, but I tend to use the b's when we're talking about the predicted values and the betas when we're talking about the theoretical parameters. Notice that there is no hat on x. As we mentioned at the very beginning of this lecture series, we kind of assume x is known or is easier to know than y. So we use the values of x to predict what y is going to be. Also note, no error. Now this is interesting, but think about it for a moment. If I make my best guess for y, that guess for y may be wrong, but it's still my best guess. So there's no error associated with my best guess. There's only error associated with the true value of y. So when I'm writing the equation for my best guess, this is the equation for my best guess. There's no error involved with it. But as soon as I'm talking about the actual value of y instead of my best guess for it, then we're going to have an error term because I'm going to be a little bit wrong. In fact, we can write the error term as how far off this equation is from the true value. Deviations from the true regression line. Are called errors. So whenever I'm talking about errors, all I mean is that there's a line that's the actual underlying correct line with all the betas, so the population line. And even in a population, even if I have all the data, the line's not going to fit perfectly. So even if I have the line from all of the data, deviations from that line are going to be called our errors. Their formula is just this epsilon character, and this is what we had before, and we calculate that by just taking the difference between our actual value and what we said before, the predicted value. Now in the population of values. Remember, we have our perfect equation. This is what it looks like when we have our perfect equation, when we have all of the data in the world. And we're still going to have errors when we have all of the data in the world, because remember, we're taking a complex model and simplifying it into something simpler. So this is how far away is our simpler model from the actual complexities of the real world. That's our error term, and it's denoted epsilon. So in considering this, think about why we can never know the errors. When we're dealing in a real life situation, when we don't have all of the population data, why can't we know any of the real errors? And this comes because we never actually know what these values are. These are values if we had all the data in the world and did this calculation. But we're just going to have a sample. We're going to have our guesses at what these values are. So we might have some guesses as to what the errors are, but we aren't going to actually have them in almost all of the data that we analyze. That said, though we can't know the actual values of the errors, we can estimate those values by plugging in our estimates. So recall, we just did something where we were talking about how are we going to estimate, or how are we going to denote estimates for beta 0 and beta 1. If we plug in those estimates, what we get is an estimate of our error term. So again, we're not going to know this, just like we're not going to know we're not going to know the errors, just like we're not going to know beta 0 and beta 1. But we can guess at beta 0 and beta 1, so that's how we're going to guess at the errors. So this epsilon hat tends to be denoted as E. So just like when we go from beta to B, where beta is the population value and B is our best guess with our sample, epsilon is the population value, E is the best guess with our sample. And this is just the observed values minus the predicted values. And recall, we had notation for observed and predicted. Our observed values were y sub I. Our predicted values were y hat sub I. So that's another way of denoting this, is the difference between observed and predicted. And then one last thing that you can look at here is this y hat. Well, we had the equation up here. Y hat sub I is just b0 plus b1. So we can also write the observed errors, or the best guess at observed errors, as y minus, and we have to remember to put parentheses here, b0 plus b1x. And this is our best guess at the error terms. Again, just like here, we had the theoretical error terms with our theoretical regression coefficients. Down here, we have the actual observed error terms, or our best guess at the theoretical error terms based on our best guess at the regression coefficients. And that's all we're doing, is we're taking something from the population, and again, in your previous statistics courses, think mu, like the population mean, and we're actually guessing at it with data, think x bar with the mean. The estimates of the error terms are called residuals. So you'll hear a lot about this term. This is going to be an important term. We're going to talk about it over and over and over again in this class. But when we're looking at the estimated errors, that is the observed values, what the actual outcome was, minus our best guess at it, the predicted value, y hat, that difference is going to be called a residual. Now this has been a lot, but let's visualize the difference between an error and a residual. And visualizing this difference comes from understanding the difference in our regression lines. So let's go to this blackboard, and I'm going to get some grid paper here. And so let's say we have a grid. And then we're going to draw on here a couple of different lines, and I'll use some different colors. So let's say orange is going to be this line here. I guess we'll go out to there. And this will be the predicted line. So this is our best guess at y hat, and this is going to be based on predicted values from the data set. So I got some data, and I made my best guess at this line. Now let's say purple isn't going to be the best guess line. Purple's going to be what the actual line is if I had like all the data in the world. So if I had all the data in the world, my line would be this expected value of y equation, which doesn't use these b values. It uses the beta values. So this is my perfect equation if I have all the data in the world is purple. Now let's assess a color. Let's do green, and let's look at an actual data point. So this is my data point, this green dot up in the top left side of the corner. Now the distance between the green dot and the orange line, the orange line is our best guess using data. So this is our residual term. That's the distance between our dot and our best guess prediction for that dot for a given x. The distance between that dot and the actual line, this is going to be our actual error term. So our epsilon, our error, our e, the residual, come from the distance between the actual data point, this is going to be an actual data point, y sub I, and the predicted data point using the orange equation. That's our best guess from data, or the predicted data point using the purple equation. That would be the best guess if we had all of the data in the world. So the difference here is visually the difference between residuals and theoretical error terms. It's what we're comparing against. One quick note I should make, and this is something called assumptions. You'll hear me talk about them. We will have entire chapters where we go through statistical assumptions. You don't have to worry about these too much, but you'll see why I'm talking about them here in just 1 second. So first of all, what are assumptions? Assumptions are, well, that literally is what it says. It's a concept or a series of concepts that we assume in order to make our statistical models work. And they're assumed for all statistical models, and it's in the theory of the model, so we're not talking about it right now. We'll talk about it later. We need to check the assumptions, and again, we'll talk about how to do this later. We'll have a whole chapter on checking assumptions. But the reason I'm bringing them up now is assumptions are made on the error terms. So when we talk about assumptions, and we will later on, and again, all these assumptions are saying is like, well, up in the model, and actually we've even thrown this out there, a couple of them, so that you can see that we haven't hit on them yet. For instance, we've assumed that the errors are normally distributed. Well, we should probably check on that. So in making that assumption on the error terms, we need to check them, and we check them with our best guess of the error terms. We check them with the residuals. So thinking about this theoretically, we make assumptions about errors, but we can't observe directly the errors because, again, we don't have that theoretical model. We don't have our actual betas. So what we're going to end up using is these best guesses, these epsilons, to test our assumptions about the error terms. All right. Now we're going to get into some of the estimation details on regression. The big question here is, how do we find the best line? Now this may seem like a weird question, but let's illustrate this quickly. If we move down on our graphic here, if I have a particular data set and I have a whole bunch of different points drawn out on this data set, how do I determine which line is better than one another? Which of these is the right line and which of these is just kind of close? How do you pick between all of these different lines? That's the question that we have to do. And more specifically, what we want to do is create a perfect mathematical calculation such that we get the exact point where it crosses over in the y-intercept, and we get the exact rise over run so that we get the perfect slope. How do we determine that best line that we can select? It's a hard question. It's a hard question. And there's several different ways to solve this. So how do we decide among an infinite number, truly infinite number of lines? Well, there are a couple of methods. I'll mention two of them. The least squares error, LSE, so least squared error is what LSE stands for, or least squares estimation. And then ML stands for maximum likelihood. Maximum likelihood. We're going to focus on least squared error in this particular class, but maximum likelihood is a very fancy and broadly ranging technique that you can also use. They're not too different from each other and both are pretty useful. In least squared error, we do exactly as the name suggests. Find the line with the least squared errors. So we square the errors and look for the line with the smallest ones. That's it. Pretty straightforward. So with the goal to minimize the error, we are trying to minimize the theoretical error term. Now consider that this is true for all i's, right? We have an error for every single point. So we don't just want to minimize a single point's error term, we want to minimize them all. So instead of just looking at one, we look at the sum of all of them. So the sum of all from I equals 1 to n of these error terms is what we're looking to do. Now, if we write this out just a little bit, we can see that this sum is the same as the sum of y sub I minus the sum of beta 0 plus beta sub 1 x sub I quantity squared. So this is something that we did before, where we looked at what is this epsilon. Well, epsilon is the difference between the observed and the predicted values. Now these predicted values right now, because we're looking at the epsilons, that is the errors, not the residuals, are something that we can't find. But theoretically, we can find the beta 0 and beta 1 that correspond to this solution. That is, we don't have to resolve this every time we have a data set. We don't have to plug in new numbers. We can solve this equation directly. How? Well, it's actually pretty simple, and you're going to get to work on a problem on one of these problems in your homework. But you simply find the derivative and solve for the parameters. So if you remember, in a continuous curve, the derivative, setting the derivative equal to 0 on a squared term, that's a parabola. If we set it equal to 0, that says where's the peak? And depending on if it's facing up, that would be the peak the most, or if it's facing down, that would be the minimum, the least. In this particular case, because this is going to be a positive quadratic, this is going to be a minimum that we're searching for. So if we find the derivative and set it equal to 0, then we get the smallest error possible. And again, you're going to get one of these. It's going to be a little bit simpler, but you'll get one of these problems on your homework where you get to practice solving this. Real quick, we'll go on and skip to the solution here. The solution can be written beta 0 equals, or excuse me, the solution, yeah, we can write this, y bar plus beta 1 x bar and then for beta 1 the solution's a little bit longer. I'll go on and type it in. Here we can see that the beta 1 equation is the sum of x sub I minus x bar, so just the mean of the x values, times y sub I minus y bar, just the mean of the y values, divided by the sum of x sub I minus x bar quantity squared, which is actually the same thing as the sum of squares of xy divided by the sum of squares x. When we're talking about sum of squares, this is a term simply means adding up the variable minus its mean squared, typically. Now note that the sum of squares of xy is this is the definition of the sum of squares of xy. This is the definition of the sum of squares of x. So if you're confused as to what the sum of squares of x is, well, it's x minus the mean quantity squared. With two variables, it takes on a bit of a different meaning, because instead of taking the variable minus its mean squared, you take the variable minus its mean, and instead of multiplying by itself, which is the same thing as squaring, you multiply by the second variable minus its mean. Maybe one more thing that we can mention here when we're talking about sums of squares is that the sum of squares of the error, which is another concept that you'll see, is the sum of the error term squared. So this is the sum of squares of the error. One more thing we should mention here, these solutions are true, and again they can be solved for the betas, but very often we don't have population level data. This is true if we use population level data, but typically we use sample level data. So if we have the sample values for x and y, then instead of being betas, these would be lowercase b sub 0 and lowercase b sub 1. Note also, given the complexity of this with just a single independent variable, that these can get much more complicated as we get into more complex variables. So maximum likelihood is handy, but let's talk about a few of the properties of least squares. Least squares estimation is nice because they yield unbiased solutions. That is, the expected value of these solutions when we solve for them is the beta 0 and beta 1. Or you can think the expected value of the predictions that when we do this with real data is that beta value. This isn't always true. If it's not true, that creates what's called statistical bias, but the least squares estimation gives us unbiased. Also, least squares estimation is intuitive. We just minimize the errors. That kind of makes sense. All in all, least squares estimation is a pretty good choice and something that many people choose. Maximum likelihood in a simple linear regression actually gives the exact same answers. Actually, in every model that we will cover in class, maximum likelihood gives the exact same answers. So that's a useful component. So we talked about estimating three different quantities. We talked about estimating B0, B1, and again, these are estimates. So these equations, I guess we can copy them over and write them as the estimates. So with sample data, if we're calculating these no longer are B0 and B1, or beta 0 and beta 1, these are B0 and B1. And all that's changed is that we're using estimated data instead of, or sample data instead of population data. But remember, we also need to estimate sigma squared, our variance. This estimate is developed using the sums of squared errors that we talked about above when we talked about SSE. This is how we estimate our error variance. The definition, or the equation to find this, is our estimated variance, which is also called MSE, or the mean squared error, is the sum of squares of error divided by the degrees of freedom of the error. That is the sum of the errors. And in this case, because we're using s squared instead of sigma squared, I'll just skip the theoretical version so that we can go straight to the useful one, is the sums of squares of the residuals. So remember, we don't have the true error terms in a fit model, we just have the residuals. This would be sigma squared if we had used epsilon here, so we could use epsilon. Note that the error degrees of freedom reflect the fact that we have n observations with two parameters, that is beta 0 and beta 1. That we already estimated. So the degrees of freedom is n minus 2 for this particular quantity. In terms of notation, and this will be the last thing that we cover today, or in this video, s squared is referred to as the MSE, as we talked about earlier, and this will always be the estimate for sigma squared. Note that we will estimate the variance for other quantities, namely the parameters. So we'll be talking about the variance of beta 1 and beta 0, but we'll include notation to distinguish it. So whenever you see s squared or sigma squared, that's always going to be talking about the MSE, either the theoretical MSE for the population model with all of the data in the whole world, or the sample MSE with the data just from our sample. When we're talking about other variance terms, we'll note it. So let's say we have s squared, and then we'll have something like a sub b0 to indicate that this is the variance term for the intercept. To avoid too much confusion, we'll typically just say MSE when referring to S squared.